Hey folks, this is Tom, your frugal prepper. This is going to be kind of a video about how I have designed my generator sub panel. I have tried to design this for two ways. First of all, you could use this design with an inverter, but it must be an inverter that is designed to be able to be hardwired. It must be a pure sine wave inverter. If you try this with like your cheap Harbor Freight inverter, you're going to blow it up. I'm not sure exactly what's going to blow, but I think it'll probably be the inverter, and I'm sure it is going to involve smoke because modified sine wave inverters are not pure 120 volts on one line. They're two square waves offset from each other on each the common and the hot that make the 120 volts potential. So yeah, this will blow them up. Okay, so what I wanted to do is I have a generator that is 120 volt output. Someday I probably will upgrade to one that does 240 volts, but mine's not worn out yet, and I'm going to keep using it until it is completely worn out because that's why they call me the frugal prepper. Unless one day I happen to be driving down the road and somebody's throwing away a 240 volt generator. Which wouldn't surprise me, somebody don't know to change the oil in it or something, and it won't start because the oil low switch thing's on, But anyway, so this is how I'm going to do my 120 volt breaker. Now, one option here is always just get a separate fuse box and kind of do the same thing, but only power half of it. Only power one bus, okay? I, however, wanted to keep my circuits balanced across both buses in normal operation mode so that it's running off of both sides of the transformer. Now, what I'm going to do is just back up a little bit, and for people who don't have a good idea how electricity works in the home, try to explain just a little bit about it. Now, let's take all of this stuff on this side of the picture over here and just disregard it. And let's just pretend that this is your standard breaker box coming into your home, because it'll be laid out kind of just like this. There's usually a big fuse at the top or the bottom, a big circuit breaker, I should say, not fuse. So that that's 100 amp or 200 amps or 250 amps. That's your main service comes in. Now, a lot of people incorrectly refer to these two separate buses as two different phases. They are not two different phases. They are one phase. This is single phase electricity. Three-phase electricity is what's running up on the poles. And every once in a while, they do step that down into three phases for commercial type stuff that requires usually large motors. However, for residential, I'm sure there's probably one out there somewhere, but I haven't yet to see three phase coming into a residence. So this would be most typical homes. It's single phase, but it's two legs. And they're called legs because there's two separate legs coming off the transformer. Transformer is center tapped, so that each side has 120 volts, but both sides between the two sides, there's going to be 240 volts. And maybe one day I'll draw another picture to show you how that works. But if you hear somebody talking about phases and they're talking about residential, they're probably talking about legs, okay? But that's just an important differentiation I want to point out. So anyway, you have 120 volt potential on bus A and 120 volt potential on bus B. Now when I say potential, that means if I take bus B to the neutral bus, between bus B and the neutral bus, there's 120 volts potential. I mean, there's 120 volts there. Okay? Between bus A and neutral, there's 120 volts. Between bus A and bus B, there is 240 volts of potential. Okay? So, that means when you come down here, all these single breakers that just hit either bus A or bus B, those are all 120 volt breakers. When you have a double pole breaker like this that hits both and feeds feeds both wires, these are usually going to an electric dryer, a range, a hot water tank, something that takes a lot of electricity. So you use both buses to get the 240 volts. The reason that you want to run 240 volts is because when you up the voltage, it requires less amperage, and so you drop the amperage, you drop the gauge of the wire you have to run. So for some things that require a whole lot of watts, you want less amps and more volts to make those watts, and because you can run thinner cable. However, for everyday circuits, we keep it 110 volts. And probably the theory was that that's a little safer. Although in Europe and many other countries, they only run, like 240 volt stuff. Um, However, we still do the 110 volt thing. Okay, so that's kind of just a general overview of how this works. This is your breaker. If you pull too much current out here, this breaker trips and it disconnects the electricity. So this wire goes from one plug in your house to another plug, up to a light, to another plug, right? This is what's actually running the different circuits and plugs in your house. And it pulls it off of both sides of the transformer. So if I ran a 110 volt circuit over to here, and then I ran all these off of just bus A, just the red ones, and I skipped every black one. Okay, the problem with that is that now I'm putting the load of all of the circuits I want to power on generator on just one leg of the transformer. I'm not dividing my load up evenly for the wires coming into my house. Okay, so if I have a 100 amp breaker on the top of my panel, that means that at some point bus B is going to hit that limit and trip, even though bus A may not be heavily used anymore. And so you want to kind of keep stuff balanced across both buses. And it's also good for the transformer, but even though you're not responsible for the transformer, when it blows, you're going to be without power until they decide to come put a new one up. But normally what you'll have in most neighborhoods is like a 6,000 volt line or 8,000 volt line. And then some transformers hang down off of that line. And then that transformer will power 5 or 6 houses. And then there'll be another transformer coming down to power the next 5 or 6 on a street. So, between all the different houses, it's pretty well balanced. But I like to keep my stuff balanced and using both sides. So, what I did was set up this sub panel box. It's basically just another breaker box. I'm using Square D QO. I have a Square D QO load center now, and my sub panel is going to be another Square D QO load center. Anytime you say load center, you're talking about a circuit breaker box. These are also called load centers. And so what I've done is I basically put one of these 50 amp breakers in my main box. And I've run two number 6 gauge wires over. And I chose to go with 50 amps because 1, I had the breakers. 2, I already had some 6 gauge wire. And it is rated for 50 amps. So I run that over to this main breaker. Okay. And right now I'm going to kind of just skip the whole ground and neutral bus. We'll talk about those in a minute. But so the power comes in to these two breakers. Or on these two poles on this breaker. Okay. Now there's a mechanical interlock here. And what this does is make it so if this breaker is on, this breaker has to be off. And if this breaker is on, then this breaker has to be off. They cannot both be on at the same time. That mechanical interlock is very important because if you forget to flip this breaker before you turned on your generator, when the power comes back on, your generator and the power company are going to get into a fight with each other. And typically, the power company has bigger generators than you do. And so your generator is going to turn into a molten ball of flaming gasoline flying across your yard. Okay, it's going to be bad. Google like generator fires. You can see some pictures of where this has happened, and it just totally melts these things down. I mean, you have like all this fighting going on inside the generator. Head the thing melts down. It's got a big tank of gasoline on top of it. You can imagine what happens. Um, so you want to make sure this mechanical interlock makes sure this is a NEC approved way. NEC is the National Electric Code, by the way, to hook up a generator is with a mechanical interlock that is NEC rated. Okay, and this one is, and it's made by Square D specifically for QL load centers, and it's $30 for a little piece of metal that keeps you from turning the breakers off and on together. So they're pretty proud of it. They charge quite a bit for it. That's probably one of the most expensive parts of the whole project. It seems like. Well, maybe the wiring, but I already had the wiring. So now I have both legs feeding from my other box. So when this is on, this leg coming from the other box feeds this here. This leg coming from the other box feeds the bus B here. Okay. And all is well with the world. All these circuits are receiving power. They're coming back out. As long as I'm not drawing more than 50 amps between all of these breakers, this breaker will not blow. I will be happy with the world. No one will even know that there's stuff's coming through a sub band. Okay. All of a sudden, power goes out and there's no more feed coming into this box. This is dead. I come in, I flip the interlock so that this breaker's off and this breaker is now on. This little breaker right here, this 15 amp generator bus B feed breaker, will always remain on and can always remain on. Okay. So now I flip that. Okay. And now let's take a look at what happens with this other breaker. So this is where I would plug my generator in outside. It will now be feeding electricity into this pole of this breaker, which will power the black bus B. Okay. And I'm like, yay, it's powering bus B. But that's only half of my circuits. How do I get the other half powered? Well, my original thought was, oh, well, we can just go and tie a wire onto bus B, get a piece of 12 gauge, tie it into that lug for bus B, run it around, and hook it right here into this breaker, and it would backfeed and feed bus A as well. And that would be just fine while we were running on generator, because if something shorted out in this wire that's running between here and bus B, if something shorted out, well, it wouldn't be any big deal. It would be 12 gauge wire, the 15 amp breaker would blow, everything would be well with the world. However, when running on mains power, when the power is on and this breaker is feeding the circuit, what happens if this breaker gets left on? Of course, it would blow because this would be shorting it. Okay. However, if this breaker is off because of the mechanical interlock, would prevent it from being able to be on, and this wire is running around here to bus B, and this wire decides to come loose from the breaker down here and touch the ground side of the box, or touch a ground anywhere, all of a sudden you have a potential 50 amps trying to come across a piece of number 12. So my next thought was, okay, Mr. Electrical Inspector guy, I will take and run a piece of 6 gauge around here, right? And then I'm set. It'll still blow the breaker. I'm ready for 6 gauge. Except that they don't make a 15 amp breaker that's NEC rated to take 6 gauge wire. I can't go up to a bigger breaker here because I'm only running 12 gauge wire out here to my generator outlet. So I have to keep this at 15. Unless I want to buy a whole lot of very expensive wire to go to my generator outlet, then guess what? You can't get a 120 volt generator receptacle that's made NEC rated to take 6-gauge wire. So here's the solution that they came up with for me. Was to put in another 15 amp breaker here. This breaker now ties these two together. Okay, so now if there was a short, or say this was to come loose during normal operation, and this part was hooked up, this wire came loose. Okay, it's not going to short out or go crazy or do anything weird because it's off. If this is on, this is off. There's no power coming out here. However, this one is still coming back, but this is off, so it won't short these two buses together. Now, if this one came loose and touched ground, you would have a short. But guess what? It's a 15 amp breaker. That's a 12 gauge piece of wire. It'll handle the short long enough to blow the breaker. So we've covered all of our bases as far as stuff coming loose and potentially shorting out. Okay, now, anytime you run a sub panel per NEC electric code, I'm not exactly sure why this is. I think it has something to do with like if you had two appliances that were on either part of the sub panel and something happened and you were touching them both or something. I forget exactly how they explained it. But even though in your main breaker box, your neutral and your ground are almost always tied together, and that's perfectly acceptable in the main breaker box to tie those two together. Whenever you run out to a sub panel, you have to isolate them. So the two buses won't be tied together inside the box, and there will have to be a separate wire coming over for the ground and a separate wire coming over for the neutral. Back at the main box, those will still be tied together, the two buses. However, it has to come up to the new box on two separate wires. I'm not exactly sure why that is, but that's the code. So that just means I run two extra pieces of number 6 wire. I have enough to do that, no problems. And so, there we have a perfectly acceptable and safe way to hook up your generator. So when the power goes out, I will come and flip the mechanical interlock over. Okay. Then I will come and turn all of these breakers off. So they're in the off position. Then I will come out, start up my generator, let it warm up, plug it in so that it's now providing power up to this bus and then comes across this bus. Okay, so it feeds the black bus. The black bus comes down here to this breaker, feeds back in here through this breaker to the red bus. So I'm powering both buses. And now I can come and flip on these breakers over here one at a time until my critical circuits are powered in my house. And I'm now running on generator in a matter of a few minutes rather than having to pull out 200 extension cords and run cords all over the place and trying to plug different stuff in. I now have a very simple way to power the house. Like I said, one of these days I want to get a 240 volt generator. So how does that work then? Well, when I run this wire, this is going to be a piece of 12 gauge going out to the generator receptacle. I will go ahead and run a wire with an extra conductor in it. Okay, that will not be hooked up today. When I change to 240 volts, I would hook up that extra conductor, and then I would have a second wire that would just come straight into this breaker here, and this 15 amp bus feed breaker would go away, and now this breaker would be feeding both sides of the panel. So that would be a perfectly acceptable thing to do. Another thing that I think is perfectly acceptable to do would be if you have 220 volt generators. I do. One smaller one slightly bigger one. You could probably leave this out altogether and not tie the two buses together and power one bus with 120 volt generator and one bus with the other 120 volt generator. So that might be an option if you want to run more circuits. That's just not what I decided to do though. But this is just kind of a safe alternative to chopping off a cord and trying to make a double pronged, a double male pronged cord to backfeed through your house. Because that stuff's just not safe. It's a fire waiting to happen. It's an accident waiting to happen if you forget to turn breakers off. If the plug falls out and your child picks it up and puts his hands across those prongs, There's live voltage coming from the generator. Um, so I just don't think that those are safe and good ideas to use. I know a lot of people do it on a temporary basis, and I don't fault you. Just be careful and make sure you keep an extra good eye on it if you do. I want something that's going to be a little bit more foolproof and safe so that people can't mess it up if they're trying to do it. And mostly if I'm under stress and tired and the house is messed up from a big storm, I don't want to mess it up, you know. So that's why I do this. Anyway, I'm going to kind of put together a list of the parts and materials and part numbers. I pretty much got everything I think at Home Depot, but I'm sure you can get it all at Lowe's and stuff too. But I'll probably put just like a Home Depot part numbers below on everything, and you can cross-reference it from there if you want to, just to give you an idea of what I'm using. I will tell you that Square D QO makes this mechanical interlock. There are a few other companies that make mechanical interlocks. Now, there are some aftermarket companies that make some. Just make sure they are NEC rated. Um, and But there's not a lot of other companies like GE, Siemens that make mechanical interlocks. And Square D only makes it for their QO line, their higher end line of breaker boxes. They do not make it for their home light line. So that's something that you need to make sure before you go buying stuff, that you can get the mechanical interlock that you need first, then buy everything else you need. Ideally, if you can get uh, whoever your main panel manufacturer is also makes a mechanical interlock, that's who you want to go with, because you can reuse all these breakers out of your old panel. Otherwise, you may have to rebuy these, and that could significantly bump up the cost of the project. Anyway, feel free to ask me any questions, comments. If you think I missed something or should have done something differently, feel free to comment below. I'd like to hear your thoughts and input on this. And if anybody else has any questions or needs a little bit more explanation, be sure to leave a question down below. Thanks. This is Tom, your Frugal Prepper. Everybody be happy and frugal out there.